Okay, so now that we have the idea, so we do know what are the components, the convolution, pooling, flattening, and the final MLP. These are the components that we have. We also do understand that we go deep, we are getting larger and larger receptive field, and this makes us talk more about the input. And this idea was the essential idea. I'm gonna give you a very quick history later at the beginning of chapter 5. So started with Leonard practically. So Leonard was the first one which did it, but gradually like different architectures were proposed, and the one which is very famous and just collected attraction of many people into deep learning was the AlexNet, right? Which was in 2012, and it could win the ImageNet challenge. And because of that, like, it got super popular, and everybody started to talk about deep learning. Now, this guy that you see used to be a kind of trend in 2014, 2015, that time. And this is VGG-16. As I said, I'm going to give you a quick history about that when we want to talk about the skip connection in the next chapter. But right now, the key point is that like this architecture is able to do pretty much any sort of classification that you can, like a basic classification that you can think of. It can do it very, very well. And this was somehow designed for ImageNet classification. Do you know what is ImageNet? No worries, we're going to talk about it in chapter 5, but have you heard of it? Yeah? Do you know what is the size of the input? Looking at this guy, oh, you don't have it right now, right? So I have it here, but you can, this is the input, 224 by 224. That was the resolution of the image. 224 pixels times 224 pixels. It was 3-channel RGB image, right? Do you know how many classes it has? 1,000. 1,000 different classes. So it's a very giant data set. It was a kind of challenge data set up to some point. People were designing, spending the whole year designing an architecture which is just going over ImageNet and doing the classification, and then they report their accuracy, and the one who is just getting the best accuracy was winning, right? And this was one of the winners in 2014. And the idea here is that like you have one image which is 1,000 different classes, different animals, objects, vehicles, human being, other things. And then at the end of the day, you want to get it, and you want to get the output, which is just giving you the class of that image, right? And this is the architecture that is working. Now, in this VGG, they are using 3x3 filters at some points, I guess. Yeah, it's 3x3. It's 3x3 pixels. And then, filters, and then they are doing padding in order to keep the dimensions fixed as they wish. And now what I want to do for you, I want to go over this architecture layer by layer, and then you hopefully can just apply the knowledge you gained up to this point on this architecture, and this is going to clarify many other things for you, okay? So what you see here in this one, and I'm going to zoom it in. So here is the input, right? This input goes over first set of layers, then second set of layers, and so on, right? And then the input is initially one 3-channel image, 224 by 224. And then you're going to get a bunch of 2 convolutions, basically. 2 convolutions without a stride. So a stride is 1, right? So it's not going to change dimension. It's only increasing in the number of channels. So the first one is 64 channel. Here is again 64 channel. After that, you're going to shrink. You do a pulling. And the pulling is happening with the stride 2. So you're just reducing the dimension of every map with factor 2, right? So you still have 64 maps, 64 different channels, but you're dropping the map size by factor 2. Now you have a smaller maps, 64 of them. You initially had larger maps, only 3 of them, right? Now you start from this guy. Again, you do a bunch of convolution, and you increase your map number of channels, right? Now you're going to get 128 channels. And from the 128 channels, once you did convolution to convolution, then again you do a pooling with a stride 2, which is going to again shrink everything with a factor 2, right? So this means that you started with 3 channels, 224. You got 64 channels, 112, half, right? And now here you're going to get 128 channels, but each of them is now 66, right? You see that every map is just shrinking, but their number is just increasing. Again, you do the same thing. Here you go factor 2 up, right? 256, and then you do 3 convolutions. You end up here 256. Again, you do just, I don't see it here, but again, you do it with a stride 2, right? So you're going to just shrink that as well, right? I think it's, maybe it's a stride 3. So let me just see it here. Oh, it's actually not, yeah, sorry, it's a stride 2, sorry. It's not 66, it's 56. So, yeah, of course, half of 112 is 56, sorry, my bad. So 56, then again, you do it with a stride 2, and then you're going to shrink the map again, right? But you are increasing, right? So you look at it here, you started with 3 maps. You ended up having here, I mean, when you do it for the last time, you end up having 512 different maps, right? Different channels. But each of them is now very small. It's 14 by 14. And actually, in the very last layer, it's going to be 7 by 7, right? So 7 by 7, every single map is having only 49 different pixels, right? But now you have 512 of them, right? And then after doing that, you just flatten and process it with 2 different layers to just get your output. Now let me just increase the size, zoom in a bit here, and then this is hopefully making things a bit more clear. So yeah, you just look at the inputs. So here is the input, as I say, is 224 by 224, 3 different channels, right? All right, this is RGB image. And then the first thing that you do this convolution. Now, you might tell me why it's written 2D convolution, because people who implement to any kind of convolution that we do, they call it 2D. I'm going to talk it at the very end of the chapter for you, because your convolution is moving 2D, right? It's not going in depth anymore. Can we do it? Yes, we can do it. It's not very popular kind of convolution, but you can do it. You can do it in 3D. You can do it in 1D. It's totally your choice, right? But right now, you just forget about this 2D here. It's just a basic convolution, exactly the same convolution we had in the course. Now, this guy is 3 by 3 filter, right? And now, you're looking at the output. You see you have 224 by 224 maps, 64 different channels. One question, did I do 0 padding here in the input before I do the convolution? Yes, I definitely have done 0 padding. I exactly have done it symmetric with 1 row and column, because 224 is not changing, right? And if I do it by 3 by 3 filter, then I am losing 2 rows and columns. So if I just add all around it 1 set of zeros, then I get rid of that issue, right? Everybody's cool, right? Okay. Now, I have 224. Every single of these filters, how many channels they have? No? What is the number of channels for this filter? 3, right? Because your input has 3 different channels, so this filter is 3 channel, right? How many of these filters I have? 64, right? So you have 64 different filters here. Then these 64 different filters are computing 64 different channels for you, right? Now, once again, you go over a convolution, right? You do your next convolution. Look at this convolution. Now, the input is 64 channels. The output is 64 channels, right? And the filter is still 3 by 3. This filter, 3 by 3 filter, how many channels does it have? No. It has 64 channels, right? Because the input is 64, right? You see it, right? Your input, your input is not anymore your original input. Your input is now the output of your first convolutional layer, right? And your first convolutional layer, you're going to have 64 different channels, right? So if you want to do convolution on that, you need filters with 64 channels, right? So this guy, which is 3 by 3, is 3 by 3, but it's very deep now, right? 64 different channels, right? And then it's going over your image, right? It's scanning it. Everybody's cool, yes? Now, how many of them I do have? Again, 64, right? Because the output channel is again 64. Yes? You still do zero padding, definitely. 2 rows and 2 columns, but you just do it symmetrically all around it with 1, right? Everybody's cool? Yes?
Make sure every convolution has an activation.
Yes, after every convolution layer you do activate, definitely, yes. It's again like the basic layers, right? If you don't do activation, it's like one giant convolution, so you need to do activation, definitely. Yes?
So for the first convolution layer,
yes.
we have a 3 times 3 filter. The size is
right.
3 times 3, and then it has 3 channels.
Right.
And then there's 64
of them.
Of those
exactly.
Channels 3 times 3.
Exactly. Yeah. And here you have 64 filters, each of them 64 by 3 by 3.
Oh.
Yeah? Everybody's cool, yes? Now what I'm doing, next thing, I am just doing pulling, and this pulling is done by a stride 2. How do I know that this is a stride 2? Because the dimension is now half, right? Everybody's cool, yes? So it means that every map you see, you just look at like batches of 3 by 3 batches, right? And then you just collect the maximum one, then you jump to the next one, right? And you so go on like this, right? And if you need, you just add 0 around if you need, just to make sure that the size is fixed, right? So now after doing that, this is going to be your first output. Now this guy is now 112, so the map is smaller, but you have 64 of them instead of 3, right? And now the next thing that you do, you again keep on doing the convolution, right? Now this guy, the top one, is giving you as the output 112 by 112. That is the size of every map. And you have 128 of them, right? 128 channels, right? Now, looking at this output, this is your output of the pulling, which is getting convolved and then giving you that new output. Now, the fact that you know the filter is 3 by 3, what is the number of channels for every single filter? Is it still 64, right? Because you have 64 different maps at this output, right? Now, how many of those filters you have? 128, right? You have more, right? Everybody's cool, yes? Now, again, from that one, when you come down, you see that you have 128 channels. So you're going to have filters here in this middle convolution, right? Every single filter here is 3 by 3, but it's 128 channel, right? And then you have, again, 128 of them. Each of them is computing one of the maps for you, right? Then you do the pulling. Everybody's cool, right? So you see what is happening. So every time that you go on in depth, you are just increasing the number of channels by a factor 2, and then you are reducing the map size by a factor 2. Yes?
I'm just wondering, what's the difference between in each convolution layer, between the first and second convolution?
Because you convolve and then you activate, right? It's just you add nonlinearity, right? Exactly like MLP, right?
And so it'll maintain the same dimensions then?
Sorry?
Like
you keep the same dimension. Like this is the proposal. You can change the dimension as well if you wish, but this somehow turned out to work fine. And like people spent a lot of time till they found out that this is working fine, right? But the key reason that these two cannot be merged is simply the activation, right? Because it makes it nonlinear. Yeah. So, questions? So now, as you see, each time that we go in, deeper and deeper, we are just increasing the number of channels. So you see we have now 256 different channels, and then we shrink the size of every map. For the next one is 28 by 28 times 512. So again, we increase the number of channels we have by factor 2, and we reduce the size in every respect by factor 2 as well. And we keep on going till we are in this last layer, right? In the last layer, you start by 14 by 14 maps. Each of them is 512, we have 512 channels of them. You keep on doing the convolution still by 3 by 3. This is the one I told you. So usually you don't care anymore nowadays about the size of your filter. You just keep it small. 3 by 3, 5 by 5 is okay, right? But because you are able to just go deep enough. And then right now that you are here, you get this 14 by 14, and then you do your last pulling, and then the thing coming out of this pulling is going to be 7 by 7, 512, right? So you have maps 7 by 7, very small, right? 7 pixel by 7 pixel, only 49 pixels in them, right? But you have 512 of them, right? Now, every single pixel in every single of these maps is looking at the whole input image that you had, right? Because you have gone deep enough that the receptacle is practically looking over the whole thing, right? It's not hard. You see like 3 to power 2, 3, 4, 5, 6. Like it's very quickly you're going to grasp the whole image, right? Now, at this point, this 7 by 7 is roughly looking, every single map is roughly looking at your complete input image, right? And you have 512 different of them, right? Each of them somehow extracted the feature using different set of weights, right? And those weights, different set of filters, right? And those filters somehow try to do the convolution in a way that they extract some specific features, right? Now, you can actually visualize this guy. For example, you can draw a heat map for every single of them. And you see one of them is just somehow very focused on one part, right? Every single of them has different visualization. It simply indicates that every single of them is looking at your image from different perspective, right? Maybe one of them is talking about the edges of your image. Maybe other one is just talking about the intensity changes inside the image. Maybe another one is talking about the specific curvature inside your image, right? And these information, of course, they are not obvious, clear for us. What do they mean? But they are clear for your MLP, right? Your MLP somehow gets this idea from these outputs that, okay, inside this image I see too much curvature. I don't see any edges. I see a contrast, a high contrast. I see, I don't know, some points where lines are crossing, and then it concludes, well, this is 8, right? Because 8 is curved and it's just crossing at some point, right? There is no edges in 8, so it should be number 8, right? For example, right? So this is the way that this guy is going to conclude. And then at the very end, once you are over here, you are going to do flattening. So you get this 7 by 7 by 512. And if you multiply it, it's 49 by 512. Just do the multiplication. It's going to be 25088. And I do know it because I just did it right before the lecture. Yes?
So from this 14 by 14 by 512 to the up convolution, why don't we increase the channel?
Here? Yeah, I mean, as I said, this is the choice, right? People who designed this architecture, they decided to do that, right? You could increase, but they somehow concluded that 512 channels are enough. Okay. Yeah, this is their conclusion, yes.
So as we go deep, we are harder to humanly understand what's going on.
Right. It's harder to explain what is happening, right? You get intuitively what is happening, but it's harder to elaborate or showcase what is happening.
If you don't know what's happening, how do you design the dimension?
The dimensions, people usually do it by testing and validation, right? So you can choose different, like a hyperparameter tuning, right? But people, if you start working with this stuff, gradually over time, you start to get the feeling, right? Like, for example, you do see that they are just reducing the size by factor 2, but increasing the number of channels again by factor 2, right? And this is somehow to compensate for that, right? I mean, obviously, you're not compensating by the same rate, right? Because you have here, like, you reduce the size by factor 2 in every single direction, right? So it means that the number of pixels is dropping by factor 4, but you're increasing the number of channels by factor 2. So in general, you're reducing, right? but at the very beginning you started with your image and you somehow massively expanded it, right? You made 64, right? And then these 64, then you started to just lose from them, right? Because you would say like 224 times 224 maps that I had only 3 of them. Now I'm just making that factor 364, right? Now this thing that I'm computing is having much, much more numbers, parameters as compared to the input, right? So it's like a lot of outputs, right? And then I want to all of them are features, right? But obviously some of them are correlated, some of them are useless, right? I need to somehow find a smart way to get rid of those, right? And this is the way that you're doing, yes.
Okay, so firstly, so what you just said, because you're increasing the number of maps, so you're trying to find maps that are useful features, realistically,
Right.
out of that list? Okay. Secondly, I was wondering, no, because what I was asking earlier was, you showed a convolutional layer as a set of neurons, and so
Right.
I saw that it was like a weighted sum and then
Right,
activation, but there was only 4 outputs on the activation, like it shrunk. It went from,
right, right.
I don't know how many we have, 9 to
Right.
4?
Yes.
So then how does it happen where it ends up outputting the
Yeah,
same number?
but here we are keeping things the same, right? We are doing zero padding, right?
Okay.
So here 28 by 28 is getting to 28 by 28.
So 28 outputs as well.
Exactly.
Okay.
Actually, 28 by 28 outputs, yeah, 784 inputs, 784 outputs.
Right, 'cause it's flat.
Yes, yes. Yeah. If you think like that, right, right. Yeah.
So in practice, like this, we use pulling to reduce the image size.
Somehow, yes. But you could simply randomly drop things, or you could do pulling. Then pulling is much more efficient because it's just filtering out your features, right? You are not just randomly getting rid of features, right?
And for like, I forgot the terminology for that, but maybe like the filter for pulling or the pull.
Yes,
pull,
yeah, pulling filter.
It's also like more of a channel, right?
Actually, here, since you don't have parameters, it doesn't matter really, right? So you actually get like, say, 64 different channels. You do pulling the same way on every single of them. You copy it at the output. You really don't, you don't really need to do those kind of, depth calculations anymore. Yeah.
We usually do increases in channel when we do up, like when we do convolution, right?
Yes, we typically in the first layers increase in the, as you go deeper, you usually increase in the number of channels. But as I said, like at the very first layer, you just giantly increase, right? From 3 channels to 64, right? But then you did it step gradually, 2 by 2, right? So you can't think like at the first, you looked at this very dense image, and you tried to somehow extract as much information as you could, right? And then you said, okay, obviously not all of them are useful, so I want to get rid of them, right? But how can I get rid of them? I start to just increase the channels but reduce the size, right? Each time you shrink the map by a factor, effectively by factor 4, right? Because 2 by 2 reduction, right? So you're reducing the number of pixels by factor 4, but increasing the size of your number of channels by factor 2, right? So it means that generally practically from first layer on, you're actually losing pixels, right? But you're doing it in a smart way, like you've initially just made.
We did pull it.
You're right.
Okay.
Yeah.
Okay, I see.
Yeah. No worries. So everybody's clear? So now at the output of the pulling, you have this guy, 7 by 7 by 5, 12. And then when you do the multiplication, you're going to get this number, 25,088, right? This is the number of pixels that you have in your very last pulling, right? That giant tensor is now having this much of entries. And then you just flatten them into a vector. Then you do just one layer of fully connected here, right? So this fully connected layer has 4,096 different neurons, right? And then again, you do another one. So dense here is simply fully connected. And it's called dense, obviously, because convolution is a sort of a sparse, right, kind of connection. Now it's dense simply means fully connected, right? And then again, you have 4,096 different neurons. Then at the very last layer, you have 1,000 different neurons, right? Or 1,000 different outputs. Do you know why you have 1,000 outputs? Yes. Classes, right? So you want to get that 1,000. You want to pass it through one softmax, right? And that softmax gives you a probability distribution over the 1,000 different classes, right? And then you're going to take the one which has the highest probability, right? Everybody's cool, yes? Yes.
Where does the 4,096 come from?
4,009, the number, you mean? Yeah, that simply just, again, this is design, right?
Okay.
But this, this number is 2 to the power 12, right? So it's like 4 times 2 to the power 10, 4 times 10, 24, right? Yeah. No, you can come up with your own number, definitely. But like as I said, people, I mean, obviously, if you should change it to like 4,100, nothing gonna change, right? Obviously, why they chose it is simply because it's a power of 2, right? That's easier usually because you can group things in a factor 2. But there is no, I mean, if you go from 4,000 to 1,000, maybe you see obvious difference. But like a few neurons change, it's not going. It's just a choice, right? Questions? No question? So now I told you the architecture is called VGG-16, right? And the main reason is because the number of layers that it has, right? 1, 2, 3, 4, 5, 6, 7, then 10. Then 13, 14, 15, 14, 15, 16, right? So it basically has, in the first round, 2 convolution, again, 2 convolution. Then you have 3 batches of 3 convolutions, and then you have your final MLP with 3 layers. So in total, it has 16 layers. We do not count the pullings as layers because basically they do not have any parameter, right? They're just shrinking and filtering or maps, right? And then this is called VGG-16. We have also VGG-19. It has 19 layers, right? Everybody's cool? Yes.
The extra layers are just like 3 more rounds to come with a layer of 3.
Convolution is more convolution. We are going to talk about this guy in chapter 5 because VGG was the point where people started to feel like, oh, we cannot go deeper because we are seeing gradient vanishing. And then the idea of a skip connection came, which made us like ResNet 1001, right? You have 1001 different layers, right? You still do not lose gradient because you can skip the connections. But we're going to talk about that. Questions?